probability is the science of uncertainty. So we are going to approach this business of uncertainty from a very scientific perspective, in the sense that yes, we know that we can't predict exactly what's going to happen, but in an average sense can we say something, right? Can we make predictions which are useful? These are very general sentences which cannot make be more specific right now, but as we go along, hopefully you will understand what exactly, how we can quantify uncertainty, right? The whole business of probability is a quantification, right, of uncertainty. You can even use that. All this English is, by the way, very important, because without English, all the maths, let me say it right in the beginning, English is about as important as the maths to describe a scientific result, right? So the words finally are the ones that are used to conclude a paper, right, or introduce a paper or a technical idea and so on, right? The maths is only in the intermediary part. So that way I hope that this definition that it's a quantification of uncertainty, actually it captures, right, the essence of what probability theory is all about, right? And this course is a first course as we as the name suggests, it is probability foundations. The electrical engineering bit is added just to say that yes, most of the course is not going to be something which is specific only to EE, but here and there we will take examples which are very relevant to EE, right, which may not have been done in the maths courses. I will mention these examples as we go along, right. The prerequisite for this course is basic calculus. First year calculus, both single and multivariable calculus, right? Multivariable calculus includes single variable, obviously, right? Ability to work with summations and integrals, right? So let me put double integral because, we will very quickly get to that, right? Single integral calculus alone is not going to be sufficient, right? At least integral in a plane, right, which involves two variables, right, you should be able to do, and which includes changing variables and so on, right? All those things will come to life in a big way out here, right? This is basically the tools that we will be using. And the goal of this course is a precise, right, it's a intuitive but precise introduction. Why do I say intuitive but precise? Because it's just making it intuitive will mean throwing out rigor and precision out the window. No, right? It has to be both. Otherwise, it's not worthy of being taught to at a college level, upper undergraduate level, third year and fourth year students, and even PG students benefit from something like this, right? But at the same time, it has to be intuitive also. If it's just precise and it just goes to the mathematics without giving intuition, that also doesn't help engineers, right? So it has to be a combination of both intuition, strengthening intuition, and being precise and as rigorous as possible. Now, in this context, I must say that of late, this advanced courses in probability theory require even more mathematics than what we'll be seeing here. We are not going to get into that, right? Like topics like measure theory and so on, which are needed at the next level, will not be part of this, right? Because it's a UG course or entering PGs, right, at that level, and so we will limit the mathematics to that, right, and the mathematical ideas to basic calculus. Okay, so the textbook which gives a very this introduction to probability. This is a complicated name. I think I spelled it correct. Yes, I think that is what it is, right? The second name is somewhat unfamiliar to us Indians out here anyway, but anyway, I think it's spelled correctly, right? So you, those of you that have not seen this book before, you can take a look at it, search for it online, and if it's possible, you can take it off the shelf, right, and use it to whatever extent you know that works for you, right? We're not going to be covering everything in this book, right? But the tone of this course is going to be very similar to the level of the material in the book, right? Okay. So what is this? What is the starting point, right? It turns out that virtually all probability courses, they start with the idea of a random experiment, right, and a sample space, right? So then you have a sample space. What is this sample space? Okay, why do we need it? All that will become clear when we define what the random experiment basically, right, is an experiment that you can perform, but you cannot exactly control certainly you cannot control the outcome, right, or it's something that nature throws at you or some other persons do, right, which you cannot control, right, and the experiment itself must be repeatable under nearly identical conditions, otherwise the probability is of limited use to describe it, right. So the probability can really come to your help only if the experiment is fundamentally, if it's repeatable under nearly identical conditions, right. The same experiment should happen in the future, otherwise any analysis you do of what's happening now is not going to be helpful in predicting what's going to happen tomorrow, right. So that is the strength of probability, or in a way it's also the weakness, right. It relies on the experiment being repeatable. So the experiment must be repeatable. So each run of the experiment must happen with the same set of the same conditions, right? In other words, right, the environment for running the experiment must be the same, right, and different runs of the experiment are called trials, right. So you have what are called trials of the experiment, right. The word so each time you perform the experiment, you get an outcome, a result. So the result of the experiment is called an outcome, right. The trial results in, or it ends with an outcome. An outcome is the most basic, right, observation that you have, right, the result that happens when you do the experiment. Like for example, the simplest random experiment, the non-trivial random experiment is tossing coins, right, which all of you have seen since high school, right, and and the classical theory goes, well, a coin can only come up either heads or tails, right. At this point we are not concerned about any probability, we are just identifying outcomes, right. So what is then, coming back to sample space, what is this sample space? Basically it is a set of all possible outcomes, and that enumeration of all possible outcomes is actually in some cases a little harder than you think it is, right. Right. So the sample space is the enumeration of or collection of all possible outcomes, and obviously then, right, straight away brings in one of the fundamental prerequisites to deal with probability theory, which is sets, the idea of sets, right, because I have used that word set right in the beginning, right. So, the sample space is therefore the universal set, right, for that particular experiment, right. So, this, right. So, let me not, so please note that I will just write universal set here. If I keep, I will write minimally on the board, but enough I hope to, right, make the point. And the notation we are going to use for this, which is typical in set theory, is this capital omega, right. Now, there is again, for electrical engineers, you all know that this symbol is a more commonly used version for what? For resistors, right, ohm. But in this course we will not have the need to look at resistors and capacitors at all, right. So, we can go back to the original. I think the usage of omega is for the sample space or is even older than its usage as a resistive element, but anyway. So, we will use, right, this notation rather than a letter like S or something, because we can save the S for some more mundane quantity, right. Okay, so we will exclusively use this omega, right, which is a very important quantity for us because it tells us all the possible outcomes without, right, saying which is more likely or less like, nothing of the sort. It just simply lists, right, it is only a list. Okay. So, the elements are listed without any particular ordering, right. You can use whatever order you want. Remember, in set theory, right, a set consists of some collection of objects without regard to order, right. Okay. So, that fundamental idea will be very important here, right. Right. So, now the question is, of course, as I said earlier, in some cases, in some real world experiments, right, you're not even sure exactly, what do you mean by the set of all possible outcomes. Not every experiment is going to be as simple as, rolling a coin or rolling a die or whatever, or some combination of them, or rolling 2 coins or a coin twice and so on, right. Not every experiment is going to be like that, where you know ahead of time, yes, this is only possible, right. But the theory does not say anything about, right, how, the theory does not concern itself about the actual physics of any experiment or what any experiment is going to come up with. So, there are 2 distinct parts which I think we should be aware of right from the beginning. One is the mathematical angle, right, the other is the physical part of it, right, and we have to keep them separate. The physical part is, which is specific to an experiment, is, as I said, listing, doing the experiment number of times, listing the outcomes, and then some rare outcomes may show up once in a blue moon, but right, unless they happen, you do not know if they are there or not, right. Let me not get into examples right now, but there are certainly very, lots of experiments with rare outcomes which happen once in a while, and some even more rarer than others, right. So, this listing of outcomes is actually, right, not as trivial as you think it is, okay. Okay, but mathematics, right, does not care about how difficult it is to obtain any data, right, it only cares about, okay, you give me an omega, I will work with it, that is, right, what mathematics can do for you, right. So, in this course we are mostly concerned with only mathematical manipulations, right, not the collection of data, right. So, we will not concern ourselves, this is a good point to say, the limitations of this particular course, right, like most other courses around the world, right. In this course we are not going to worry about how we actually got a particular mathematical model. It is there, we will work with it, right. This is the mathematical model. 99% of our, I might even go as far as to saying 100% of the examples here are going to be, right, of that nature. This is the mathematical model, what can we do with it, right. So, where this what actual physical situation is really well modeled by this model, that is not a question we are going to answer here by and large. Occasionally we might say, well, this is used in this physical case, so that is used there and so on, but that is not the focus of this course, right, just like other courses at this level, right. So this is okay. So that the reason why I am emphasizing that is because this is a good time to say it, right. So mathematics deals with omega and its subsets, right. So once you have a universal set, you can look at subsets of omega, right. What are these subsets of omega? That is a very important thing about any sample space, right. A smaller collection of outcomes. Omega is a collection of all possible outcomes, somehow you listed them, fine. But what is of interest in many cases is what are the subsets you can form, right, from a given sample space, right. What do these subsets correspond to in practice, right? They correspond to what we call events. Now the word event is used, right, when I also just for clarification I am just going to when I say use the word prob, I mean probability, not problem or any other expansion of prob, right. In probability theory, events, right, is a term used for subsets. It is a very specific use of the word event, right. I guess when the theory was being developed, they needed a word to express ideas like, right, for example, if you roll a die, right, the event that an even number shows up, right, which is a subset of the sample space, right. If you say the sample space is the numbers 1 to 6, which is all the numbers that can show up on the die, right, the getting even numbers, the set of even numbers is a subset, right, and so on and so forth, right. So you can appreciate that the bigger a sample space is, the more points it has, the more subsets it will have. So our fundamental starting mathematical calculation is this, right, given that I have, right, supposing I have I am going to here, from next time onwards I will try to be more organized on this board, right, but please bear with me, right. So let us say consider omega with n discrete elements, right. The most basic examples of in probability or even in set theory for that matter, right, are discrete sample spaces where you can count. If you have enough fingers in your hands, feet, whatever, right, you can actually count n, 100, 200, whatever. Those are examples where you can actually count. And there is also extension to countable infinity, right, which corresponds to the set of integers 1, 2, 3, infinity, right. That is also considered countable. So countable is, right, a synonym for discrete, right. So in this case I am saying, well, it has a finite number of elements, right. Countably infinite obviously is where that n goes to infinity. Okay. How many distinct subsets can you form? What are distinct subsets first of all? Distinct subsets are subsets which differ at least in one element, right. If you look at 1, 2, 3, 4, 5, 6, you look at 1, 3, 5 and 1, 2, 5, they are distinct because 2 is, right, not the same as 3. And again in defining a subset, you do not care which order you wrote them, right. 1, 3, 5 is the same as 5, 3, 1. Ordering of the elements in the set makes no difference, right. So you also have, by the way, the concept of equality and difference of two sets. Two subsets are equal if they consist of exactly the same elements written whichever order, right. Okay. So now I am asking the question, right, if there are n discrete elements in the sample space, right, how many subsets can you form, distinct subsets? The key word is then, I mean, we will not use this, automatically subsets are going to become the useful subsets are going to be distinct, but for now I will write that word down, right. How many? 2 power n, everyone knows this, right. How do you get, what is the simplest way of getting to that number 2 power n? This is very important. I hope this is viewable, right. I think it should be, there should not be any problem. Unfortunately it came to the bottom right there, but I am assuming that okay. So where did this 2 power n come from? Each element is either in a subset or not in a subset, right. So if you form strings 1 0 0 0 1 1 0 0, so for every element you put a 1 or 0. How many strings of length n can you form? 2 power n with n bits, right. So it is as simple as that. You also include in this count of 2 power n two very important quantities. One is the all zeros where nothing is included. What is that set called? This 2 power n includes the empty set, it also includes the all ones, which is the sample space itself. So let me talk about empty set. The count includes and it also includes so for every sample space we have every non-trivial sample space which, right, contains at least one element, right, you have an empty set. Of course, a sample space with one element is not a very interesting sample space because that's only if that's the only thing that's going to happen, there is no point in constructing a theory around it, right. So in a way the most non-trivial, I mean the basic non-trivial sample space is 2 points, head tail, or 0 1 0 1 in a different context, right, or whatever, two distinct outcomes, right. So empty set is a set that contains no elements. I have to write this down because again it is a very important concept. So definition, empty set, I just write it as phi, right. This is again very standard notation. So you can be used in every experiment, right, regardless of what sample space you have, you can always, right, formulate a set which has no elements, right. So phi is in a sense it's common to all sample spaces. Okay. So we have this very important calculation 2 power n, right, and each of these 2 power n including phi and omega itself, right, can be considered an event, right. In at least in the discrete case we are going to consider the, there is this fine line we have to draw. I'll talk more about this fine line, about actually what sets can be, right, what events can be included in our list, special list that we are going to talk about, or not included, right. There is a distinction there, but for the discrete sample space, right, we will include all possible subsets, right, we will every subset of omega as event, whether or not, right, it makes any physical, whether or not this makes any physical sense to us or not, right. For example, if you roll a die, the numbers 1 4 and 5 may not mean anything physically, or 1 and 5 or whatever, right. You might say what is the point, why do we want to include it, but for mathematical completeness it turns out that, right, it is important to precisely define what is an event and what is not an event, right. And right up front I want to say, right, for discrete sample spaces we will basically allow every subset of that sample space to be called an event, okay. And So this okay, what was I going to say, I am getting okay. So if you have n points, now coming back to that example of n points, how many sets have that one particular element, right? Okay, before that let me write the notation, right? Omega. So now I think it's important to introduce notation for the points in the sample space, right? So omega with n points, we will notate it like this. Omega 1, this is the standard way in which this set is written with curly braces, right? So the same notation we can use, right, for the subsets also. We just use only, right, the smaller set of elements, right, which are included in that the elements of omega which are included in the in a smaller subset as that. So subset e.g. some subset say A, which can be omega 1 comma omega 2, whatever, just an example, right. So this notation, the reason I am doing this is to emphasize that these curly braces will occur a lot in this course, right. Okay. So continuing with some more terminology, right. So basically we are saying now that outcomes of the experiment, right, are the elements of omega are outcomes of the experiment. That is basically what we have said so far in different words, right. Are identical to the elementary outcomes, right. Whenever you are talking about outcome, remember, right, it is the basic observation you are making which you are including in omega, right. So obviously the elements of omega must be are the same as the elements of outcomes of the experiment, right. And so this is like a summary. So this elements, so then subsets of omega are events, right. So this is like a compilation of some terms, right. So omega itself, this is in the probability, right, jargon, as you might call it, right. In the jargon of probability theory, these on the right hand side we will list a few things, right. What is omega? What is the probabilistic jargon for omega? It is a certain event which is going to happen no matter what, right. And phi of course is the impossible event which can never happen. Why is phi called impossible? Because some outcome has to happen, right. So you can't have any trial of the experiment where nothing happens. One last thing before I conclude for today, right. How do I say that a particular event has happened on an experiment, right? If an experiment has these n outcomes in the sample space, right, and I define my subsets. See, these subsets have to be defined and named and all. I mean, if you want to associate a name or a title, you should do it beforehand, right. You say even number on a roll of die, whatever, or a square, whatever. So you identified that event or that subset earlier. Then if the outcome of the experiment lies in this subset, if it, right, the outcome, remember, as on every trial of the experiment you cannot get both omega 1 and omega 2, you can get either omega 1 or omega 2, it is not possible to get multiple outcomes, right. That is the fundamental theory. So if either omega 1 or omega 2 happens, if it shows up in the experiment, then you say the event A has occurred, right. Since I am running out of time for today's class, I will stop here.